Hello everybody, thanks Tyler for introducing moment of inertia. Now I'm going to introduce a similar concept called radius of gyration. So gyration sounds weird, but just imagine it as rotating around an axis. That's really all you have to imagine it as. And I want you to draw the same graph that you did before with the x, y, z. And I want you to draw it again with that same rectangle lamina. So a high-level understanding of what the radius of gyration is if all of the mass in this lamina was concentrated at one point, the radius of gyration would be that the place where you push it and it goes where you most want it to go, either around the x-axis or around the y-axis. And the radius of gyration is that point where all of the mass would be located in that one spot. However, rather than being related to center of mass, it's more related to inertia, which is why we get the formula for radius of gyration. So the actual definition is that if you were to choose one point on this lamina, it's the point where the moment of inertia is the same as the lamina as a whole. But that's kind of a weird definition to grasp. So all I ask is that you know how to use the formulas and you know how to apply them. So about the y-axis, would be an x value, remember, because if it's along the y-axis, you have x values to where you want to rotate, where the mass is concentrated around this so that it changes how it rotates around the y-axis. X double bar, which is what the radius of gyration is notated as, equals the square root of the moment of inertia with respect to the y-axis over the mass. And it is the same thing for the x-axis. And like I said, it's more related to inertia than center of mass, which is why the formulas look this way. So about the x-axis, again, it's a y value for the same reason, and it's the moment of inertia with respect to the x-axis for similar reasons, but I'm not going to go into those reasons right now because I think it's more important just to know how to do it. I'm going to go straight into an example now. Example 4. Find the center of mass and radii of gyration for lamina with a mass density rho equals rho of xy equals y, and occupying the region of the points 0, 0, 3, 0, 0, 2, and 3, 2. So that's 0, 0, 3, 0, 0, 2, and 3, 2, if you can't read it. First, let's graph it. That's always the first step, at least when you can. So you know that all the points are positive, so you can forget about the negative axes. First point is at 0, 0, 3, 0, 0, 2, and 3, 2. So you get a rectangle, which is nice, because when you integrate over it, it's really simple, and all of the bounds are just constants. So in this case, this is what the rectangle would look like, and sometimes this is impossible to do, but in this case, the mass density function is rho of xy equals y. So we can, if you try to visualize that, it would mean that the density gets higher as the y value gets higher. So this would be 2 and this would be 3. That's a 3. So if you'd want to draw it, the density would look like this. As you get lower, the density gets lower too. So just keep that in mind. You might have some ideas about why I mentioned that, but we'll come back to that after we do the next thing that's always on up on the list of things to do. So first, if you can, graph it. Then find the mass. Finding the mass is almost always the first thing you want to do. In this case, it doesn't really matter if I want to integrate like this or like this, but in this case, I will go like this. So the outer bounds would be 0 to 2, the inner bounds would be 0 to 3 of the density function y dx dy, which is equal to 0 to 2. This is with respect to x, so it would be y times x from 0 to 3 dy, which is, and that would just be 3y, so 3y, integral of that would be 3y squared over 2 from 0 to 2. And if we think about that, that's just 12 over 2, which is equal to 6. So the mass in this case was 6. I'm going to erase everything now just to have more space. Besides this, I'm going to keep the graph up really quickly. So the mass is 6. Okay. The reason I kept this up is the first thing that we wanted to do is find the center of mass. And sometimes I tell you that there is symmetry when the density function is constant. In this case, it's not constant, but you can still see a symmetry from left if you cut a line right there. So if you were to actually cut a line through the center, the mass would be equally concentrated on both sides. And you can see that geometrically with this picture. And the place where that is, the x-coordinate, is just, which would also be x bar, because the center of mass is 3 over 2. You could just do 3 minus 0, divide that by 2 to get the center. So x bar equals 3 over 2. Remember that that was also my over the mass. So now we don't have to do some more integrals and find my. All we have to do is find mx to find y bar. Okay. So I'm going to erase this. And the next step is to find mx, m sub x. Okay. Mx is the integral from 0 to 2, 0 to 3. Since it's m sub x, around the x-axis, it depends on the y-coordinate, so that's why we have y, times the density function, which is also y, and it's dx dy, because 0 to 2 is the y. And that's equal to 0 to 2 of y squared times x from 0 to 3 dy, which is equal to the integral of 0 to 2 of 3y squared dy, which is also equal to y cubed from 0 to 2, which is equal to 8. So we have mx is equal to 8, and we know the mass, and we know x bar. So we have everything we need to find the center of mass. Center of mass equals x bar, y bar equals 0, 8 over 6, or not 0, sorry, 3 over 2, 8 over 6, which is just 3 over 2, 4 over 3. And there's our answer for center of mass. Now we're actually going to move on to finding the radii of gyration. I'll just write it here, radii of gyration. First, we need to find the moments of inertia because that was in the formula for radii of gyration. And I sub x is, we can just do the same integration from bottom to top. So it would be 0 to 2 for the y, 0 to 3 for the x, and then the formula is y squared times y, remember that formula from Tyler, dx dy, which is equal, and these integrals are pretty easy. And I'm just going to jump right to a few steps ahead, which is from 0 to 2, integral of 3y cubed dy, because x would just be a constant from 0 to 3, so you just multiply that by 3, and then which is equal to 3/4 y to the 4th of 0 to 2, and that comes out to be 12. You can take my word for it. I sub y is the same thing, except with x squared times y, dx dy, which is equal to the integral from 0 to 2 of y times 1/3 x cubed from 0 to 3 dy. I'm going to put that back over here, which is just equal to the integral from 0 to 2 of 9y dy, which is equal to 18, and you can take my word for it as well. These integrals are fairly simple, so I'm not going to go over them too deeply. So now we have ix and I sub y, 12 and 18 respectively. All we have left to do is plug those in for the formula for radii of gyration, and we have our answers. So remember, x double bar was about the y-axis, and that was equal to I sub y over m, which was equal to 18 over 6, the square root of 18 over 6, so square root of 3. Y double bar was about the x-axis, which was equal to I sub x over the mass, which was equal to 12 over 6, which was equal to root 2. And there we have our final answers. I'm not going to go over any more examples because we have the homework to do that. So thanks. That's our lesson.